The United States is one of the most advanced countries with respect to safety standards. 75% of worldwide deaths from fire occur in the United States, which makes it the highest fire death rate of all developed countries. There are some 5,000 fire-related deaths and 300,000 fire-related injuries annually. Majority of fire deaths occur not in areas with high concentrations of population, but rather in the residential sector in the single-family dwelling. This demonstrates our successful efforts to create a safe environment for large commercial and high-rise structures. Similar attention has not, unfortunately, been devoted to creating safe environments for the residential sector. 80% of the fire-related deaths that occur in the United States occur in the residential sector. 45% of these deaths claim those who are over 65 years of age and the very young. The location of residential fires is attributed primarily to 4 rooms: the kitchen, the bedroom, the living room den, and the garage. While the origin of many fires is unknown, sources that have been identified include matches, heating equipment, overloaded electrical equipment, hot embers or ashes, cooking equipment, water heaters, and electrical wiring. Predominant fuel sources include wood, grease fat, cotton, rayon materials, and paper. The National Fire Protection Association is an international technical and educational organization that was organized in 1896. Its goals include the promotion of fire science as well as the improvement of methods of fire protection and prevention. It is estimated that 75% of American homes are equipped with smoke detectors. Of the detectors present, according to the National Fire Protection Association, 30.01% were operable, 16.82% were unoperable, and 53.17% operational status was unknown. Researchers at Texas A&M, working with a grant administered by the Texas A&M Research Foundation and provided by the MasterGuard Corporation, has conducted an independent study to investigate the effectiveness of various detection systems typically used in the residence. The research team, through full-scale testing, sought to compare and evaluate the performance of 3 types of detection systems typically used in the home. These include heat detectors, smoke detectors, and sprinkler heads. The investigative test included systems exposed to 3 fire scenarios: smoldering type fires, open flame fires, and kitchen grease fires. In order to conduct these tests in a true residential setting, an unused 2-bedroom house located in Taylor, Texas was made available by the MasterGuard Corporation. The house was a wood frame structure containing 2 bedrooms, 1 bath, a kitchen, and a living room. A covered porch was located adjacent to the living room at the front of the house, and a small pantry-type enclosure was located off the kitchen at the rear of the house. The primary objective of this research project was to determine the effectiveness of the current NFPA 74 code requirements concerning the minimum standards of fire detectors in the residence. Another objective in the study was to determine how different environmental conditions, such as heating, ventilation and air conditioning, ceiling fans, or door to the room of origin in an open or closed position, will affect the performance of fire detectors. The drawing is a representation of a typical furniture layout. The actual test scenario was centered around a small grouping of furniture, which included a stuffed chair with rayon cotton fabric, a coffee table, an end table and table lamp, carpeting on the floor, and drapery covering the window. Because the existing house did not have a hallway, an area was taken from bedroom number 2 and a wood stud wall enclosure was constructed. The corridor would also serve as the route for air to be returned to a newly installed air handling unit. The unit was installed in a closet adjacent to the newly created hallway. A return air grill was located on the wall of the hallway. Flexible ductwork was installed to permit air to be distributed to the living room and the kitchen. The ductwork in the hallway was enclosed to protect it from fire and smoke. Because bedroom number 2 did not play a role in the test, it was employed as a control room housing video and other photographic equipment. Air quality and additional temperature monitoring equipment was also located in this room. A double glazed opening was created at the wall facing the living room to permit visual observation of the fire progression. From this room, all activities related to conducting each living room fire test would be controlled and monitored. A trailer was brought to the site to house the data monitoring equipment, which was the interface between monitor circuits and the recording computer. The data monitor, which monitored continuously, was connected to a computer that recorded the data on the hard disk drive. Because many test burns were to be conducted, it was necessary to harden the interior in areas where the fires were to take place. This would permit numerous fires to be set without causing excessive damage to the building. Fire retardant gypsum board was installed on the walls and ceiling in the burn area in the living room. Because the intensity of the fire that would occur in the area of the window location would cause the glass to break, the window was covered with fire retardant gypsum board. 3/4-inch plywood was installed to protect the floor. In order to measure obscuration, flood lamps were installed at 2 different levels in the living room and hallway. Photoelectric sensors located on the opposite wall were connected to a data recorder. Prefabricated panels housing the various detection devices were mounted at 2 locations, equal distance from the fire, on the living room ceiling. Because many residences employ ceiling fans, a fan was installed to determine what effect, if any, its operation would have on the performance of the detectors on the fire growth. Fire retardant gypsum board was also installed on the walls and ceiling in the kitchen. Because of the nature of the grease fire, no particular damage to the floor was expected. As a result, no protection was applied to the floor. The National Fire Protection Association recommends that a smoke detector be located in the bedroom hallway of each residence. One of the objectives of this study was to determine the relative speed with which the various types of detectors located in the bedroom hallway would respond to the products of combustion from different types of fires when the fire originates in an adjacent room. By locating panels of detectors in the hallway as well as in the room of origin, the relative reaction time on each detector at all locations could be correlated. The furniture layout in the living room consisted of items normally found in a residence: a stuffed chair with rayon cotton fabric, an end table and table lamp located adjacent to the chair, a coffee table located in front of the chair, carpeting on the floor, and drapery covering the window location. A wicker waste basket was located between the chair and the end table. The smoldering fire test would be conducted in the living room and would employ a 602-degree Fahrenheit heating element as the heat source. The heating element would be inserted between the seat and back cushion and connected to an electric circuit. The flaming fire test would use the wicker waste basket containing 1/2 pound of newspaper as the fuel source. The kitchen grease fires would be conducted by heating grease in a cast iron skillet on the stove. The fire detector devices to be tested were mounted on prefabricated panels. These panels were installed at 2 locations at the ceiling of the living room, equal distance from the point of origin, at the center of the bedroom hallway, and near the center of the kitchen ceiling. The intensity of the heat and smoke generated in many of the fire scenarios would be great enough to cause the various detectors to alarm and, in most cases, render the detectors unusable for subsequent test. Additional panels were fabricated to replace the used detector panels. A system of threaded metal bolts embedded in the ceiling joist was devised to permit easy exchange of the panels when necessary. The first fire scenario will simulate a smoldering ignition of a rayon cotton fabric chair. The heating element utilized will be rated at 602 degrees Fahrenheit. The heating element will be placed in the fold at the back of the cushion of the chair. This test will continue to the point where all of the fire detectors have activated. The various environmental conditions in the room of fire origin and in an adjacent hallway will be documented on the data logger and computer system. The various smoldering ignition fires will be conducted with the hallway door in an open or closed position, with a ceiling fan either on or off, and the HVAC system either on or off. At 1 minute into the test, the living room temperature is 86 degrees Fahrenheit. The temperature in the corridor is 88 degrees Fahrenheit. The oxygen level in the living room and corridor is 21.8%. Smoke detectors activated 15 minutes into the test. At 40 minutes into the test, the temperature in the living room increased to 89 degrees Fahrenheit. The temperature in the corridor is 90 degrees Fahrenheit. The oxygen level in the living room is 20.5%. In the corridor, the oxygen level is 20.1%. The heating element has charred a 6-inch diameter burn into the cushion. Smoke is rising behind the back cushion of the chair. At 60 minutes into the test, the living room temperature has increased to 91 degrees Fahrenheit. The temperature in the corridor is 90.5 degrees Fahrenheit. The oxygen level remains constant at 20.5% in the living room and 20.1% in the corridor. Thick smoke is obscuring the chair. At 78 minutes into the test, the living room temperature has increased to 93 degrees Fahrenheit. The temperature in the corridor is 91.4 degrees Fahrenheit. The oxygen level in the living room has decreased to 20.4%. The oxygen level in the corridor decreased to 20.0%. Smoke is becoming increasingly yellow and green in color. The smoke is extremely dense. The lower obscuration light is barely visible. The top obscuration light and story poles are completely obscured. Air currents are beginning to develop because of heat. Smoke is beginning to boil against the viewing window. The room is completely obscured. The temperature in the living room is 95 degrees Fahrenheit. Fire is present 79 minutes into the test. Fire has reached the ceiling. Temperature in the living room is 120 degrees Fahrenheit. The temperature is increasing and the oxygen level is decreasing rapidly. The temperature at this point is 240 degrees Fahrenheit. The maximum temperature was 690 degrees Fahrenheit prior to extinguishment, and the oxygen level in the living room was 11%, and in the corridor, the oxygen level was 9%. fire was extinguished with the halon system. The Taylor Fire Department also aided in the extinguishment. To give an analysis of the smoldering type fire, the 602 degree Fahrenheit heating element melted through the foam cushion and ignited the cardboard at the back of the chair. The cardboard ignited at a temperature of approximately 450 degrees Fahrenheit. With the heated gases present, fire development was rapid and totally engulfed the living room. All the smoke detectors did receive major heat damage. The heat detectors did not receive any heat damage. Wiring in the conduit story poles that connected the detectors and thermocouples to the data logger received some heat damage and had to be replaced. Thermocouples and photocells were used in the room of origin and hallway to measure the temperature and obscuration at 30 inches and 60 inches above the floor and at the ceiling. Environmental sampling tubes penetrating the walls in the room of origin and hallway were connected to a pump located in the control room. The air samples collected through this system were analyzed to determine the oxygen and carbon monoxide levels. The previous fire indicated there was very little change in temperature during the smoldering process. At ignition, a rapid elevation in temperature was experienced. This is typical in a smoldering fire condition that ultimately becomes a flaming fire. The graph represents the temperatures in the room of origin. There was a constant rate of smoke generation, which in turn decreased the visibility in the room of origin. Very little increase in oxygen level was experienced in the room of origin until the time of ignition. As oxygen was consumed by the combustion process, the level decreased rapidly. The parts per million of carbon monoxide increased slowly up to the point of ignition, at which time the level of carbon monoxide increased rapidly. As shown in this graph, the photoelectric detectors in the room of origin, in general, activated prior to the ionization detector. The delay of the hallway detector activation with the door in a closed position demonstrated the influence of door position upon detector activation time. The characteristics of the smoldering fire do not lend themselves to the activation of the heat detector device. Therefore, a lag time in the activation of the heat detectors was experienced. The heat detectors activated within seconds after the point of ignition. The next fire scenario will simulate a flame ignition source of fire. The source of ignition will be 1/2 pound of paper placed in a trash basket. Again, the various environmental conditions in the room of origin and in the adjacent hallway will be documented on the data logger and computer system. At this point, the temperature in the living room is 96 degrees Fahrenheit. The oxygen level in the living room is 20.3%. The oxygen level in the hallway is 20.0%. first alarm activation occurs 1 minute 17 seconds into the test. The temperature has increased in the living room to 440 degrees Fahrenheit. The oxygen level in the living room has decreased to 14.6%. In the corridor, the oxygen level has decreased to 7%. The fire is being extinguished with the halon system at this point. Temperature at the ceiling is approximately 460 degrees Fahrenheit. Again, all the smoke detectors did receive major heat damage. The heat detectors did not receive any heat damage. The previous fire scenario indicated after ignition there was a rapid increase in temperature up to 350 degrees Fahrenheit in less than 3 minutes. After a brief burn time, the smoke density began to increase at a much faster rate. Oxygen in the room of origin was used to support the combustion process, thereby creating an untenable environment. The carbon monoxide increased at a steady rate, peaking out at 220 parts per million. All of the smoke detectors in the room of origin activated in less than a minute. The door to the room of origin in a closed position caused over a minute delay in the activation of the smoke detectors in the hallway. The heat detectors in the room of origin activated after approximately 1 minute into the fire. With the door to the room of origin in an open position, the heat detectors activated in less than 2 minutes. The door in a closed position increased the activation time by over a minute. The last fire scenario involves a typical kitchen grease fire. A cast iron skillet with grease was heated to the point of ignition. The grease fire was permitted to continue to the point of fire detector activation. Again, the various environmental conditions in the kitchen and hallway were documented on the data logger and computer system. The The smoke layer has lowered to the 5 to 6 foot level. The oxygen level in the kitchen is 20.5%. The temperature is 102 degrees Fahrenheit. At the time of grease ignition, temperature increased to 105 degrees Fahrenheit. The oxygen level remains at 20.5%. At the point of extinguishment by the Taylor Fire Department, temperature reached 124 degrees Fahrenheit. The oxygen level remains at 20.5%. The temperature in the kitchen increased slowly until the grease ignited. Upon ignition, there was a very rapid increase in temperature. The smoke obscuration provided for a steady decrease in visibility. The kitchen experienced very little decrease in oxygen during the grease fire. The level of carbon monoxide showed a slight increase in parts per million. Smoke detectors are not recommended for installation in the kitchen because of their false alarm characteristics. Note the quick activation of the smoke detectors. The door to the room of origin in a closed position caused a significant delay to the activation of the smoke detectors. The heat detector activated shortly after the grease fire ignited. Based on the data obtained from 16 fire tests, the following conclusions were developed. A systematic approach to residential fire protection should be utilized. A systematic detection program should consist of the following: smoke detectors located in each bedroom, smoke detectors located in rooms where doors may be closed, smoke detectors in the hall or stairwell, heat detectors located in areas where smoke detectors will give a false alarm. These include the kitchen, the mechanical room, and garage. Room of origin fire detectors provide early warning when doors are closed. Time saved by fire detectors in the room of origin averaged 6 minutes for smoldering fires, 3 minutes for flaming fires. When room of origin doors are open, hall detectors activated nearly as quickly as room of origin detectors. Central heating, ventilation, air conditioning, and the ceiling fan had no significant effect on detector operation. It is projected that future tests are needed utilizing a typical bedroom fire scenario in a 2-story residential setting. This additional research is needed to complete the evaluation of proper fire detection requirements in the residence, which, in turn, will reduce the loss of life in the American home.